here at UTD's campus for this year's CAST summer project. When we first got introduced to our project, it seemed like a daunting and seemingly impossible task.
However, with the help of our graduate students, we overcame our initial apprehension about the project.
Come on, let's go. Our objective of this project was to develop a computational model to accurately predict the thermomechanical effects of a directed energy deposition in a printed metal part.
However, in order to do that, we must first understand how metal works.
First, we headed over to Dr. Wei Lee's workspace to observe his custom-built directed energy deposition metal 3D printer, which printed out our sample builds for us. Dr. Lee's graduate students specified the printing parameters using G-codes, which acts as an interface with a computer numeric control that directly controls the machine. With this, we printed 3 separate builds using stainless steel 316L powder. The first was a single-layer single-bead build, the second was a double-layer single-bead build, and the third was a double-layer single-bead build with machining flattening the surface between the 2 layers. Following the completion of our prints, we headed over to the 3D scanning lab, where we used a surface scanning machine to create a scan of the surface of our samples.
The surface scanner gives us a point cloud, which we can convert to a mesh and export as an STL file. So what do we do with the STL file? Compare the scan information in the file with the simulated build to validate that the simulation is realistic. So what is the simulation we are talking about? Using Flow3D, a computational fluid dynamics software, our collaborators generated a multi-frame simulation of a metal 3D printed build. The simulation predicted the geometry of the build as it is printed, as well as the temperature of both the build and the substrate it is printed on. Using the simulated temperature and geometry, we can generate a model of the residual stresses and distortions in the simulated build using a software called Abacus. This serves to demonstrate the feasibility of using this process to more accurately model residual stresses and distortions. In order to transfer the simulated build's geometry and temperature over frame by frame, we needed to write a program in MATLAB, a numerical computing and data analysis platform that would accomplish that.
At the end of this camp, we learned how metal 3D printing works and how to predict stresses and strains in a 3D printed object.
This camp was a great learning experience for us, and I hope I can come back next time.
Thanks.
Thanks.